Okay, we'll pick it up just right where we left off in the lecture document. So we'll get into exactly how this idea of the central limit theorem, what it means for actually doing problems, and then what problems will look like. So I'll start with the measures and the z-score for the central limit theorem. So for a large population, many random samples of size n are selected. So kind of the fundamental idea behind this all is you've got this huge population and we have no idea what the distribution might be. Or maybe we do know what it is, but it turns out it doesn't matter if it's normally distributed or not. We can make it normally distributed if we take a lot of samples of the same size, and we'll call the size of the sample n. Okay, then we'll say the mean of each sample is denoted by x bar. So we saw x bar way back in chapter 2. If you remember, x bar represents a sample mean. Well, it makes sense. The mean of the sample we're going to denote by x bar. So then, if you look at what's next, the mean of all sample means. Okay, so again, remember we're thinking of all these sample means as if it's the data itself. So we take the mean of all means and we denote that as mu sub x bar. So mu sub x bar is the mean of all of the means. It's the average of the averages. And as we noted at the end, towards the end of the last video, the mean of all sample means is the same as the mean for the original data. So mu sub x bar just equals the original mu. All right. Now let's talk about standard deviation. The standard deviation of all sample means, okay, turns out there is a difference here. So we're going to call the standard deviation of the sample means, we're going to call it sigma sub x bar. How is that related to the original sigma? So it turns out it's the original sigma divided by the square root of n. So what is that? Okay, so sigma is the standard deviation of the original population, and n is the sample size of all of your samples, right? Sample size of the samples. So your standard deviation of all sample means is the original standard deviation divided by the square root of your sample size. And you see down at the bottom, so I say, okay, where sigma is the standard deviation, there's probably, okay. The standard deviation of all sample means, you might hear it referred to as the standard error, because we want to distinguish it from the original standard deviation. So, using the phrase the standard deviation of all sample means is kind of a mouthful. So instead, people call it the standard error. And so I may or may not refer to it that way. I usually just refer to it as the standard deviation of all sample means, because that kind of harkens back to what it actually is. But there you go. Okay. So where is this going? Well, you see at the top of the next page, it says, okay, so the z-score, when we're using the central limit theorem, we have a slightly different formula to calculate the z-score. Here it is. The z-score for any sample mean x bar is z equals x bar minus mu over sigma over the square root of n. So the idea here is, again, we're treating the sample means as the data. So instead of x, we have x bar, a sample mean. We subtract mu. We still subtract mu. Why do we still subtract mu? Why don't we change that part of it? Well, because mu is the same as mu sub x bar. So the mean of all means is the same as the original mean. But you notice what we divide by is different. We're dividing by sigma sub x bar. But sigma sub x bar is the original sigma over the square root of n, square root of the sample size. Okay, finally, this is all still probably very confusing. Let's get to practice number 1. And these are both parts A and B here, very, very straightforward. We're just trying to get used to this idea and this new way of finding the z-score and how this all connects. What would a problem look like? All right, finally, the average age of a vehicle registered in the US is 96 months with a standard deviation of 16 months. Okay, great. So we're going back to that, some vehicles, but now it's in the US, not just California. The average age is 96 months with a standard deviation 16 months. However, the distribution of the ages of these cars is unknown. A random sample of 36 vehicles is selected. So let's note what we have already. And I've got that right here at the beginning, number 1. So just even before we get to part A, so we know the mu is 96. We know sigma is 16. Now, those are for the original population. And we know we're going to take a random sample of size 36. So n equals 36. Okay, now we'll get to part A. Find the probability that the mean age of the sample is less than 100. So we're thinking, okay, from these 36 vehicles, what's the chances that the average age of those 36 vehicles is less than 100 months? Okay, so imagine 36 vehicles. Some are going to be newer, some are going to be older, some are going to be, maybe a few years old, 5 years old, some are going to be 10 years old or so. So if we take the average age of all those 36 vehicles, and you think 36 vehicles, there's probably a good spread to the ages amongst 36 different cars. So if you take the average of all those 36, what's the chances that that average is less than 100 months? How do we do it? Okay, here we go. So here x bar is 100. Right, the average is going to be less than 100 months, so we'll take x bar as 100. Then we're going to use our new z-score formula. So we'll take z equals 100 minus 96 over 16 over square root 36. So there's our formula, x bar minus mu over sigma over square root of n. And we got to calculate that. Now we want to be really, really careful here on calculating that. You could go for the whole thing in your calculator in one shot. If you did, you want to be sure, use parentheses around the 100 minus 96 and parentheses around your denominator there, 16 over square root 36. And you could just type that in just like that with those parentheses into your calculator. Or if you want to break it down, a couple more steps is helpful. We could say here the numerator is 4, so that's not too bad. And also the square root of 36 is simply 6, so that's nice. Now we could go for our calculator. Again, if you do, be sure to put parentheses around that denominator. So I'm going to show you guys what that would look like on mine here. I'll just go for the original since that's more difficult. So I would say 100 minus 96, some parentheses there, divided by parentheses 16 divided by square root 36. And here I need 2 parentheses to close that off. And there's my z-score. Turns out this one is actually pretty nice. Z here turns out to be exactly 1.5. I'll think of it as 1.50. Because, of course, we want our z-score to be to 2 decimal places. From here, we recognize, go back to the problem, we're trying to find the probability that the sample mean is less than 100. So we're going to go with, and it looks like I'm kind of giving it away here. Let me cover that up. We're looking for the probability that z is less than 1.50. So now it's really all, once we have the z-score, it's exactly the same as the things in chapter 6. And well, we'll grab our table, and just the same way we did before, we'll look up 1.50. That's 0.9332. And so we have our answer, 0.9332. So what is the chances that from our sample of 36 vehicles, the average is less than 100 months? It's over 90%, and 93.32% of the time, the average of 36 vehicles is going to be less than 100 months old. You think, wow, that probability is really high. I mean, you kind of think back to the original question, the average of all the vehicles in the US is 96. So, okay, so the average of all of them is 96. So if we just push that up by 4 months, not even a year, right? From 96 months to 100 months. You just say, okay, so what are the chances that, it's within 100? Like, that's really close to 96. Yet the probability is super high. Like, that's unexpected. You would think it'd be like maybe pretty high, but not this high. And the reason is we didn't just look at one vehicle out there. We looked at an average of 36 vehicles. So there'll be some that are a little bit older, but there'll be some that are a little bit newer, and they will balance each other out. So the average of those 36 is actually pretty likely to be pretty close to that 96. And so even straying up by 4 months to 100, it's very, very likely that the average of that sample is going to be less than 100. Okay, let's do part B. Find the probability that the mean age of the sample is less than 105 months. Okay, now we're going up even more. So what's that going to do to our answer? Okay, well, let's find out. I think I've got it on the next page. So we're going to take x bar, our sample mean, to be 105. And we're going to do a probability less than. Of course, we need the z-score. So I've got it here. Here, the z-score we find with 105 minus 96 over 16 over square root 36. And if you want to just go for your calculation right there, be sure to use parentheses around your numerator and denominator like so. I have the value there, but I'll show you what I'm doing in my calculator again. So 105 minus 96 with parentheses divided by parentheses 16 divided by square root 36, and you get 3.375. But we'd like to round that to 2 decimal places, so let's make it 3.38. And just to note, you might have decided to subtract here first and simplify our square root, so 9 over and then here, but you'd still need parentheses there if you were to do it that way. Okay, anyway, the z-score is 3.38. And then we're finding a probability, we'll cover up our final answer there, probability less than that z-score, 3.38. Now this is getting pretty deep on our table. 3.38 is almost at the very bottom. There's 3.3. There's 3.38. 0.9996. That is almost to 100%. 0.9996. You're all but guaranteed that if you pick 36 vehicles, the average age is going to be less than 105 months. Not even 1 year above the average age of 96 months. That's only 9 months above the average of all the cars. Are you serious? Okay, so here's the thing. If you were to pick one car, then the chances of it being less than 105 months, it'd still be pretty good, but nothing near 99.96%. Nowhere close to that. Right? There's a whole lot of cars out there that are over 105 months old. What is 105 months in years? That's not even 9 years old. That's 8 months, or excuse me, 8 years and 9 months. There's a lot of cars out there that are over 8 years, 9 months, right? But if you were to take, but why? So why is this probability so high? Because we're not thinking just one car. We're thinking take 36 cars and take the average of those. So some are older, but some are newer, and they balance out. And they're gonna come, when you do that for 36 cars, it's gonna come a lot closer to the original mean, right, that 96, than it would if you were just looking at one car only. Okay, now this really explains the name of this chapter, the central limit theorem. How is that? Let me show you. This is what just happened. So reflecting on our two problems we just did. Okay, so we're saying, we've got this bell curve, right? The average is 96 months, the average age. So what are the chances of being less than 100? And it was really high, right? It was over 90%. So if we were to look at all of this area below, that was what it was, 93.32%, right? So there's less than 7% is above. Actually, the way I've drawn this 100 should probably be further over to better depict what's going on. Then we said, okay, so that's 100. What about 105? And it turns out 105, right, all of this below 105 was 99.96%. It's like almost the entire thing. There's just this tiny little bit left over at the top. And truth is, I should probably move this further over because it's just this tiny, tiny little piece above. So what happened? When we use the central limit theorem, when we find all of these sample averages, what happens is, let me get rid of what I've drawn here. Okay. What happens is the original bell curve, like maybe the original bell curve for the original data would be doing this, right? That's how we usually draw it. The original bell curve, this data gets pushed to the middle, because when we take sample averages, things tend to balance out. You get some older, some younger, and it ends up pushing the data toward the middle. So when you think of the data as the averages themselves, then those averages end up pushing closer together. So central, because it's pushing together, and then the fact that it's a limit, well, it's like the limit is the center. So if you keep pushing and keep pushing, it's going to push up higher and higher to the middle like that. We're going to see some examples, some more examples pretty soon in the next video that are going to highlight this again from kind of a different angle. But that's the gist of it. So the central limit theorem, because the data is being pushed toward the center. And so now what it means is straying further away from the center is going to have much more drastic results on the probabilities than if we were just looking at individual data points like we did in chapter 6. Okay, let's finish this video here. We got more to come.